Unit 3B, Lesson 3. In this lesson, we're going to continue working with graphs of various types of functions, looking at the key features, being able to identify the domain and range for those functions, and be able to draw a rough sketch by hand. The first function we're going to work with is the square root function, y equals radical x. For this function, in its basic form, the domain and range are both going to be from 0 to infinity, with 0 being included. And for the domain, that makes sense because if we think about the square root, we can't take the square root of a negative number. So the smallest number we can put in here for x is 0 because the square root of 0 is 0. Because of that domain restriction, that restricts what our y values can be as well. So if we put 0 in for x, we get 0 in for y, which is why we have a point starting at the origin. If we put 1 in for x, we get an output of 1 for y as well, so 1, 1 we can see as a point on the graph. Next, if we put 4 in for x, the square root of 4 is 2, so we could see 4, 2 as a point on our graph as well, and you can see the general shape. This is going to continue to increase. It's just going to start increasing at a slower rate as we move to the right. Now we're going to look at an example of a square root function that has horizontal and vertical shifts. So we're looking at the function y equals the square root of x plus 4 and then plus 1. In its basic form, we have y equals the square root of x minus h plus k. The value of h represents the horizontal shift, how far left or right we're moving. K represents the vertical shift, how far up or down we're moving. So in the example we have, x plus 4 is the same as x minus negative 4. So the horizontal shift is negative 4. We would move our x coordinate 4 units to the left, and our k value is plus 1, so we would move up 1. So for each of our ordered pairs on our previous graph, we had these 3 ordered pairs that we used to sketch the general outline. We're going to move each x coordinate 4 units to the left, and each y coordinate 1 unit up. So our new ordered pairs would be negative 4, 1, negative 3, 2, and 0, 3. If we plot those points, draw a smooth curve through there, that would continue to the right, again increasing, just increasing at a slower rate. So here's our graph for y equals the square root of x plus 4 plus 1. Now we're going to look at the graph of the cube root function, y equals the cube root of x. The domain and range for the cube root function is negative infinity to infinity because we can take the cube root of a negative number. So on the basic graph, some key points are going to be negative 8, negative 2. If I take the cube root of negative 8, that is equal to negative 2. Because negative 2 times negative 2 times negative 2 gets us a result of negative 8. And then you can see the other key points, negative 1, 0, 0, 1, 1, 8, and 2. If we plot those points, draw a smooth curve going through them, we can see our basic graph for the cube root function. Now we're going to look at the transformed graph of our basic cube root function. We have y equals the cube root of x minus 2. Again, we can think of this as the basic form involving h and k. Y equals the cube root of x minus h plus k. H represents our horizontal shift and k represents the vertical shift. In this case, we have no vertical shift. We only have a horizontal shift of 2 units. So we're going to move each point 2 units to the right. So if we think about those ordered pairs from the previous problem, all we're going to do is add 2 to each of the x coordinates. So we have our new ordered pairs. We can plot those points, negative 6, negative 2, 1, negative 1, 2, 0, 3, 1, and then 10, 2. Draw our smooth curve through them. Next, we're going to look at the graph of a piecewise defined function. It's called a piecewise defined function because it has multiple pieces, multiple parts. So in our example, we have f of x equals 2 for x values less than or equal to negative 2, negative 2x for x values between negative 2 and 3, and it's equal to x for x values greater than or equal to 3. So we're going to have 3 different parts to this function that we're going to work with. When trying to graph a piecewise defined function, always start from x values to the left. So we can see we have x is less than or equal to negative 2, so we're going to graph this portion of our function, our piecewise function, first. So if we're just looking at this first part, we can think of this as y equals 2. Our function is equal to 2 for x values less than or equal to -2, which we know is just going to be a horizontal line. So graphing the first part of our function, I have a filled in circle at -2 because it's equal to -2, and this pattern for the function y equals 2 continues as x goes to -infinity. So we can see our portion of the graph, the horizontal line y equals 2, for x values going from -infinity to -2, this endpoint included, so I have a filled in circle. Now we're going to go to the second part of the function, which we can think of as y equals -2x, for x values between -2 and 3. So what we can do is plug in these x points, these x coordinates, -2 and 3, to get the corresponding ordered pairs. So if we plug in -2, we get a y value of 4. If we plug in 3, get a y value of -6. We can plot those 2 points. So we have -2, 4, and we have 3, -6. These are going to be open circles because those endpoints are not included. If we look at our domain, they're strictly less than, so they're not included, open circle. So starting at this point, we know our function was y equals -2x, so if we think about slope, down 2 over 1, down 2 over 1, that pattern continues until we get to our other endpoint. Last part, now we have to go through the f of x equals x, which we can just think of as y equals x, for x values greater than or equal to 3. So starting with 3, if I would plug 3 in for x, I get a y value of 3 as well, so I make that point first. It's a filled in circle because x is equal to 3, and then we know if it's y equals x, that's just a slope of 1, so we go up 1 over 1 and continue that pattern, and we get our line going to x equals, or as x approaches infinity, that pattern continues. So this is the graph for the piecewise defined function we started with, f of x. We broke it down into its individual parts, starting with x values to the left and moving to the right. The next graph we're going to look at is the graph of an exponential function, y equals 2 to the x. We know it's an exponential function if it's some real number with our exponent being a variable. Okay, the domain for the basic exponential is going to be -infinity to infinity. The range is going to be 0 to infinity, that endpoint not included on 0. If we look at our specific graph, y equals 2 to the x, plug in some key points, -2, -1, 0, 1, and 2. We get the corresponding y values of 1/4, 1/2, 1, 2, and 4. So if we plotted those points, drew a smooth curve through that, we get our general outline for this graph. As we go to the left, this graph is going to get closer and closer to the x-axis, but it's never going to cross the x-axis. This will never have a y value equal to 0, which we could see by the range. As we go to the right, this graph is going to increase and start to increase very rapidly and approach y values of infinity. Some of you may be wondering how we got y values of 1/4 and 1/2. We have to recall exponent properties. So if I would take 2 and raise that to the -2 power, using exponent properties, if I want to make this exponent positive, we use the reciprocal property, so I would move this term to the denominator. We could rewrite this as 1/2 squared. So when we move this term to the denominator, the exponent becomes positive. So now we have 1/2 squared is 4. So that's how we get a y value of 1/4. We would use a similar idea to get a y value of 1/2 when we plug in -1. Then we have the ordered pairs 0, 1, because if we plug 0 in for x, any value raised to the 0 power is going to be equal to 1. The last graph we are going to work with is the graph of a logarithmic function. We have y equals log base 2 of x. A logarithm is the inverse of an exponential, so there's going to be similarities in their graphs. The domain for the logarithm is going to be 0 to infinity. the endpoint not included, and the range is going to be negative infinity to infinity. So if you recall the last example, when we had the exponential, the domain and ranges are just flipped around, and that's because they are inverse functions, so the domain and range flip. Some key points to this graph: if we have x values 1, 2, 4, and 8, corresponding y values are going to be 0, 1, 2, and 3. So if we plot those points and draw our smooth curve through there, we have our general outline for y equals the log base 2 of x. Some key things to notice in this graph: as our x values get closer and closer to 0, our y values are going to start decreasing very rapidly. X is never equal to 0, which we can see by the domain, so this is going to start decreasing, approaching negative infinity very rapidly as x gets very small, close to 0. As we go to the right, our graph is going to continue to increase. It's just going to start increasing at a much slower rate as x approaches infinity. I assume the graph of the logarithm is going to be the most confusing because we haven't dealt with logarithms as much as the other functions. We will talk about this more in class, the relationship between an exponential and a logarithm, and look at the similarities between their graphs.